Good afternoon, and thank you for joining us for today's virtual tour brought to you by Region 9, KFDX, and the Arts Council Wichita Falls Area Inc. I'm Nicholas Qualla, coming to you live from the studios of KFDX. Well, it's easy to think of math as something that helps us balance our bank accounts or gauge when we will need and stop and get gas on a long road trip. But have you ever considered math can help us in our artistic endeavors as well? Well, this year our focus will be on the many ways that art and math benefit from each other. And today we'll look at how music and polyrhythms played at high speeds can create tone, chords, and even depending upon how syncopated the rhythm it is, it'll translate into how dissonant the chord will be. And our very special guest today is Dr. Sarah Cobb. She's the Assistant Professor of Math over at Midwestern State University. Welcome, Dr. Cobb.
Thank you.
So before we begin, can you tell us a little bit about how you came to be interested in math?
Yeah, my family is very mathematical, really all of us, but especially my dad. He bought a board game when I was about 4, specifically to teach us about negative numbers. And every time I said, no, I don't like math, he said, yes, you do, here's a summer program. And so every time I tried to quit math, every time I decided I didn't want to do math, he would tell me that I did love math, which was true, and push me back into it. And I think that pushing back into it when you try to quit things is part of what makes any of us good at hard things.
Now, I understand you double majored as an undergraduate in math and English. Why did you finally go the math route?
Honestly, I was better at it.
Okay.
As I did more and more math, it became more and more interesting. It became more and more the way that I thought about things. And as I did more and more English, it became more and more clear that I wasn't quite asking the right questions.
Okay.
I wasn't quite thinking from that perspective.
Okay. Now, we should mention that the math question that you're sharing with us today is one you're working on with Dr. Marcos Lopez, also over at MSU's math department. How did the two of you begin working on this, and have you partnered on other projects before?
We work on things together a lot. The two of us we've been at the department sort of the shortest amount of time. We came in around the same time, and so we work on a lot of projects collaboratively. And music is one of his great enthusiasms. It's not, I like music, but he's definitely the more musical of the two of us. And so this is something that he encountered and showed me and that we started thinking about together.
And what happens when you find the answer to these questions? Do you submit them for publication, or are these things that you pursue for your own enjoyment?
Ideally, both. We do have a lot of, we do hope to publish a lot of these questions eventually, but also it is something that we find interesting, and hopefully that other people will find interesting as well. And it's that sense that part of creating knowledge and learning things is also sharing that knowledge with other people.
Now, the actual question that you and Dr. Lopez are working on was given to me as follows. Our goal is to develop an easy way to compute syncopation for 2 beats played together. We're also interested in patterns that emerge from those computations, as well as thinking about the chords that emerge when the polyrhythms are played at high speeds. There are some terms that we should probably define a little bit, the little big terms. So can you help us through that process?
Yeah. So syncopation is probably the first thing that needs to be defined. When you play any music, you have strong beats. So there's generally some strong beat going through the music. And syncopation happens when you emphasize things that are not on the strong beat. So you can play things that are slightly before the beat, and you end up with something like, and it ends up feeling a little bit less rigid and less in step, and so you end up with that off the beat emphasis. And so depending on how you divide the beat, you're going to perceive that as more syncopated or less syncopated, more close to the beat or less close to the beat. Are there other things I should define?
Yeah. So in the benefit of being able to compute a polyrhythm or syncopation?
So when we talk about a polyrhythm, what we're talking about is 2 rhythms that are played at the same time. And so you hear not only the 2 rhythms, but an interaction between them. And when we measure that syncopation, what we're not measuring something that you need to know to play the music. You can make music without measuring this stuff. But if you want to analyze why the music has the effect, why some things sound similar to other things, having that numerical approach to the syncopation can be very helpful in that situation.
Okay. Now we're going to play a clip from a song called Chalk, T-J-A-K, not the stuff you write with, but it'll help explain what you mean by polyrhythm. And I guess this song is also known as the monkey chant. It tells the story of how a group of monkey-like creatures helped Prince Rama fight the evil king Ravana. The song is said to have over 150 different rhythms in it. So I think we have that song loaded up. Let's see. I can tell that takes a lot of practice to get down. So a lot of different rhythms there. What was shown, how does that help describe what a polyrhythm is?
So it's a really excellent example in that you have different groups of people in that choir who are playing different rhythms. And so what you hear, if you're paying attention and you've maybe seen this a few times and you start to pick out the different pieces, you see these different rhythms. And then as they're layered over one another, that's where you end up with this idea of a polyrhythm, is that you're listening to all of those rhythms at once, and what emerges is a particular kind of, it's a different effect from listening to any of the rhythms because they all interact.
Now, you mentioned that, but you also mentioned the chords that emerge when polyrhythms are played at high speed. So how is it possible for a beat of a rhythm to create a chord?
So if you play a sound fast enough, you stop hearing it as a rhythm. If you listen to a note, what you're hearing is a number of vibrations per second, and the standard A is 440 beats per second. And so if I start playing that excerpt from Chalk fast enough, you eventually hit a point where you're hearing it hundreds of times per second, and you start to hear a note. If I'm playing one rhythm, one sort of steady beat, and I'm playing another one twice as fast, those two beats end up one still you're getting twice as many hits as the other, and you hear an octave. So an octave is two notes that vibrate at twice the speed of the other. If you have something like you get one at 3 times for every 2 times for the other, that's where you get a perfect fifth. And those are both the sort of intervals that we hear a lot in certain varieties of classical music. So as you speed that up, you end up with these standard things. We hope that maybe the syncopation affects the kind of tone that you hear. We haven't gotten too far on that part yet.
So like an octave, for example, is like low C. That's an octave, and that's a perfect fifth, what you were kind of illustrating. So definitely in that sense. And also explain the dissonance that kind of makes itself apparent there as well.
So if you play something like things like a perfect fifth or an octave are things that when you hear them they sound pleasant by whatever we've been taught to hear in music as pleasant, but you can also have notes that when you hear them together they sound terrible. If you're just banging on the piano, you're probably going to find a few notes that don't sound so good together. And so we think that maybe those notes that sound less good together would come from rhythms with a higher measure of syncopation. If you're playing one note at 15 beats per second and one at 7 beats per second, we think when that's sped up, those are weird numbers. It's going to be a weird interval.
So, for example, if you all watching are familiar with The Simpsons, the theme song, The Simpsons, that's an augmented fourth. That was considered a dissonance years and years ago. So that's just one example. Now, I was a former music major, so I think it's pretty fantastic that math can assist us in understanding music. But it's the reverse. Is the reverse possible as well? Have you ever used music to help explain a mathematical problem? This
is a really interesting question, and I think to some extent anything you know helps you understand anything else you want to know. That's a very broad statement, but if you are used to thinking about, for example, these kinds of polyrhythms, there's ways that you can talk about certain mathematical concepts where whichever one you understand is going to help you understand the other one. And so for me, I use a lot of language metaphors when I talk about math. For Dr. Lopez, who I work with, he uses a lot of music metaphors. You end up using a lot of what you understand to talk about things that you're learning.
Okay. Now, do you have an example for us you'd like to demonstrate? Or do you have any questions, or should we turn over to class questions as far as what you're working on?
I'm happy to take class questions.
Okay. Let's go out to Seymour and see what kind of questions y'all have for Dr. Cobb. Anybody have any questions for as far as math and music and rhythm and? And I think you might all have to turn your microphone on. There we are.
Okay,
Yes,
we have
sir.
one question. Oh, can you squatch down a little bit? There we go.
Oh, hi there. How are you?
I'm good.
Nice and nice. Take it easy.
I was wondering, how is music and math still alike? Because I'm still confused.
How are music and math alike? So one of the things I think that both of those require is measuring. So when you're looking at music, you want to be able to talk about sort of how far apart different notes are. That's a measurement thing that's going to come into math. And so you end up splitting notes into pieces and measuring distances. You can certainly think about music without doing a lot of math explicitly, but if you know math and you know music, you see more and more where you're using that math as you think about the music.
All right. Anyone else have any questions out there at Seymour?
She said, "Thank you very much. That answered her question."
Thanks
Okay,
for your
somebody else-
question.
Anybody else? What do you have, Deacon?
Should I get the,
Yes, why don't you come on in? Make it like this. Okay.
Hi there.
Hello.
What's your question?
All right. So, was math always your favorite subject, or did you have a favorite subject before it?
Oh, that's an interesting question. Math was my favorite subject when I was very young, and then not, and then it was again, and then it wasn't, and then it was. So I changed my mind a few times, and it depended a lot on what we were doing and what I was finding interesting at the time. I also loved history. I loved reading. I loved music, and I was interested in a lot of things. But math always had a pull for me.
Thank you.
Thank you for your question.
Okay, we have
Do we have
one more
another one?
question.
Yes.
Yeah, Ruben.
Come on. Don't be shy. Hi there. What's your question?
What kind of music do y'all like?
Dr. Cobb?
I really love choral music with a lot of harmony. I sing in a choir, and I really enjoy that kind of music.
Mezzo soprano? Alto?
Usually alto.
Alto, okay. I like classical. I like jazz, which has a lot of syncopation.
Yes.
So yeah, a lot of different choices of music there. Anybody else have a question? Yes, sir.
I have a question. Does 16th notes, how do you do 16th notes in math?
So if you look at the words for the different sizes of notes, quarters and eighths and sixteenths, they're named mathematically for how small the parts are that you divide them into. And 16th notes are an interesting example because you see syncopation very naturally. If you take a group of 3 16th notes and you play that 3 16ths over and over, you don't end up getting to a whole measure. And so 16th notes are a good place to see some of that way of things that fit nicely in a measure and things that don't quite fit as nicely.
So for example, if there was a bar of 4 beats, 4 quarter notes, right? 1, 2, 3, 4. 4 quarter notes are eighth notes, and 16th notes are. That's how you break that down. Right? So there you go. So I do use my music skills every so often. Still, okay. Well, do you have any more questions, or should we move on, guys? What do you think?
I think we're ready to move on.
Okay,
Thank
great. So let's see, I want to make sure we have this. A lot of people, when they think about math and music helping each other, how do you think, how do you explain it to your students? I mean, I know we're talking to sixth graders, but how do you explain it to older students?
I don't think it's very hard to see the connection when you're looking at something specific. When I talk about nearly anything, I tend to fall into talking about it in the language of math. And that's true of music as well. And so students will ask me a question, and the way that I answer that is to bring it back to how do we think about this by measuring things, how do we use those numerical kinds of approaches.
I want to ask, because of what you do, your profession, are you constantly analyzing things from a mathematical perspective? Are you able to kind of break away from math?
I think to a large extent, math is a way of thinking about things. It's a way you want to make precise statements when you're doing mathematics. It's not so much about numbers as it is about that precision and that logic. And so you see this in the way that mathematicians talk to each other, in the way that we think about things. There's very much a sense that if anyone makes a statement that has an exception, the mathematician is going to look for the exception. Everyone knows this. No, babies don't know that. And so there's
Right.
that's a mathematical way of making that statement.
Could we ask you to give us a visualization of the question you're working on?
Yes. Yeah. So I have a whiteboard here and markers that I'm throwing on the ground. So if you can you guys see my whiteboard? No.
There we are.
All right. So if you look at, I'm going to mark that as a unit. That could be a measure or a beat. And here's the same distance. And I'm going to divide it up here into 3 and down here into 4. So I've divided that into different equal-sized parts. And so what you see, if you, when you clap this rhythm, for example, you'd end up with something that looks like this. I can't actually clap this rhythm because I keep trying and messing it up. But you end up with some beats that are very close and others that are very far apart. And so what we're interested in is, if you think of this 3 as the stronger beats in your measure, you end up with this note that's very close to the strong beat. That's going to feel very syncopated. That's easier to see. This note's much farther from the strong beat. That's going to feel much less syncopated. If, I'm going to use my green marker now. If you look at the measure being divided into these pieces, you end up with different lengths of space here. And so this question of how you measure depends on where you consider those strong beats to be. And that syncopation is always looking at what's far from those beats.
So this is a 4-measure beat, Dr. Cobb? This
is 4 beats to a measure and 3 beats to a measure.
Okay, so so this is the 1, 2, 3, 4, and I think what you're trying to illustrate is, right, over a 4-beat pattern,
yes.
Correct? Okay, so can you clap that for me?
Maybe.
Okay, so just go like this, 2, 3. So, keep going, and I'll go. You hear the syncopation, guys? There you go. So
thank you.
You're welcome. It's easier with 2 people on there.
Yes.
Yeah. Okay.
And so the question of whether you consider how far your beats are from mine or how far my beats are from yours gives you a different sense of how syncopated this rhythm is.
Sure.
Even though it sounds in some ways the same.
Okay. All right. And you could do that with not necessarily 4 beats. You could do 3 beats, 2 beats, 5 beats. It translates across. But for this purpose, we're trying to do 4 beats to a measure. Okay. Thank you for that demonstration. I think that makes it a lot easier for those of us who don't read music, or for anybody who doesn't read music. So just for fun, once you come to answer for this question, what do you think you'll start working on next? That's a lot, huh?
Yeah, we're doing about 4 things right now.
Oh, really? Okay.
So we do a lot of research. Me and also Dr. Lopez, we work together on a lot of things. So we're interested in measuring these simple polyrhythms. There's a wonderful, famous piece of music called clapping music.
It's by Steve Reich.
Steve Reich.
Yes. Yes. Okay.
And it's a very interesting example of polyrhythms where there's it shifts throughout the piece, and you hear the same rhythm played against itself in different ways. And so we're very interested in knowing how that fits into our measures of syncopation. We're also working on some education research. How do we effectively talk about math? We're working on some very, very abstract math that sort of connects to things that we did in graduate school. So we've got a lot of things on our plate, and they're all fun.
Sure.
It's a cool project.
Steve Reich, that's a very difficult piece of music to perform and to listen to. So, but I recommend it if you have a chance. Steve Reich, R-E-I-C-H, clapping music. You guys should check it out. Maybe you can practice in the classroom. It's very fun. Speaking of students, if we have students watching, and if they want to learn more about polyrhythms and how pitch and rhythm can equal each other, Doctor, where should they begin their research?
There's a wonderful YouTube channel by Adam Neely. That's Neely. He does a lot of very interesting, mostly musical stuff. This is where Dr. Lopez first encountered polyrhythms, was on his channel, and that sparked a lot of our interest and a lot of those questions.
Okay. I think let's open it up to the students out at Seymour again. Guys, I know we've covered a lot there in the last couple of minutes. What kind of questions do we all have now?
We have one coming.
Excellent. Hello there. How are you?
I'm good.
What's your question?
So what kind of math has been the hardest?
Good question.
For me, the first time I started studying geometry was very hard for me because I have trouble visualizing things. But in graduate school, I did a lot of geometry, but it's all in like 5 dimensions, so no one else could visualize it either. So that made it easier, I guess.
What other, and if I could ask you one question, I mean, I know we talked a little bit about, we're talking about difficult math. Do you ever get into more difficult theories beyond what we're talking about today?
I think everything is difficult when you're learning it. And so
okay.
in a joke that mathematicians tell is that there's only 2 kinds of things. There's trivial things and unsolved problems. So if anyone knows how to do it, it becomes easy. And the more you practice something, the more it feels like something you've always known, I think.
Okay, we have another question. Yes, go ahead.
How long have you been a teacher?
I've been at Midwestern for about 5 years, and I did a little bit of teaching before that when I was in graduate school for about 4 years. So I guess 9 years.
And while we're waiting for someone else to, well, maybe not come up. Yeah, we'll go ahead. Go ahead. What's your question?
How would you use geometry in music?
Ooh.
So one thing that springs to mind, if you think about key signatures, which is sort of different ways of arranging your notes
I'll demonstrate
to
here.
create a piece.
Sure.
Those you can easily draw those in a circle, and
I'll just draw the key signature
right.
for people who don't know what we're talking about here. So you've got like a B flat and an E flat. So that's kind of your key signature there. So, yeah.
And so there are about 12 standard choices.
Mm-hmm.
There's more than that.
Right.
But you can look at sets of 12. And when you do that, you would typically arrange them in a circle, like a clock. And you can say things about these key signatures when you look at the ones that are across from each other. You can look at the ones that make a triangle, the ones that are next to each other.
Circle of fifths, yes.
Yeah, and so there's all these beautiful relationships in that circle of fifths that are geometric when you look at it the right way.
Right, and that's a whole other study that Dr. Cobb is talking about, is music theory. In other words, we don't know, it's based upon over hundreds of years the development of how we in the Western world read music. So, yes, back again, sir. What's your question now?
Were you ever bullied for liking the things you like math or music, or were you ever teased?
Sometimes, but I had several very good friends starting in middle school who were also interested in a lot of the same things. And so the people that I cared most about, which was my family and my friends, shared my interests and were very supportive, and that's the thing I remember more, is those supportive people.
And kind of on that similar note, thank you for your question. On that similar note, how do you encourage younger students and potential teachers like yourselves to get not only themselves but young students involved in math? I know sometimes, and I'm sure some of this is can get a little lofty. So how do you get people interested in math?
That's a really wonderful question. I think a lot about that because I encounter a lot of students who are not as enthusiastic about math as I am. And I think one of the important things there is I think a lot of people find math hard and therefore find it a little bit scary. And so I think one of the things that I really try to do is tie it to other things that you learn how to do. Whatever you're learning to do is difficult, and you make a lot of mistakes. And I think with anything you're learning, it's easy to give up and not push through those mistakes. So the biggest thing that I try when I'm trying to help people be interested in math is to give them something where they can experiment and play with the math.
What would be an example of that? Could you give us one?
So we have a math club meeting this afternoon at MSU, and what we're going to do is we're going to take 5 little discs and put them in a row, and then you can move one disc on top. You can move it either left or right. And then once you have a stack of 2 discs, you can move 2 spaces left or 2 spaces right. And the goal is to get all of those stacked up in one spot out of your 5 original spots. And if you can do it with 5, can you do it with 6 and 7? And can you think of a way that you can do this no matter how many discs were in your line to begin with?
Okay. And I want to stick with this because, like I said, math was not my forte. I'll admit that freely. So when students come up to you and they ask you, how can I get my future students involved? I mean, is there an obvious scenario in life where you could just say, oh, yeah, by the way, did you ever think of this as how math affects your life?
So I like to knit. And so I used this example with a class the other day, where if I'm knitting a blanket and it starts small and it gets bigger, and it's only half as big as I want, and I've run out of yarn, how much more yarn do I need? And so I think to find interesting uses of mathematics, you start with what you're interested in, and then there will be mathematics that tells you things you need to know. And so I try to start with where that person's interested. And
perhaps we're roaming a little too far afield, but I want to ask you, do you find oftentimes when students are having difficulty in math, is it half and half as to they aren't being taught it right, or is it, and the other half being they may not just absorbing it, or is it kind of all over the map?
That's a big question, and it's something that a lot of research is being done on.
Okay.
And I think there's certainly things on both sides.
Okay.
And I think it's very easy in any subject to not learn things for the sake of learning them. I think any subject you're learning to pass a test, you're going to miss a lot of the fun and the nuance.
Okay.
And I think math tends to, unfortunately, be taught that way a lot.
Okay. What else would you like to tell the students pursuing art, and how can they reap the benefits from learning math?
So the first thing that I tell my students often ask, when am I going to use this? And the answer is, if you know it, all the time. If you don't know it, never. And so nothing you learn is useless. Anything you learn is going to connect to the things that you want to know most. And if you find math difficult, or you prefer other subjects, then you also, by pushing and learning that thing that's difficult, you learn sort of to take ownership of what you're learning. You learn to push through those difficult things. And so I think math can help you become a better learner in a lot of ways.
Okay. Well, Dr. Cobb, we want to thank you so much for sharing your expertise and your experience and your passion, really, for math. So, again, thank you so much. And we also want to thank Dr. Marcos Lopez for his work on this, and a special thanks to Dr. Dale Heidebrecht for the video clip of Chalk. And thank you for watching, especially our students out in Seymour today. for our virtual tour. We thank you for watching, and thanks, of course, to KFDX for making this possible. Join us again next month. Yep. Thank you, and thanks. Join us as we next month as we show how math helps the Red River Quilters Guild. Speaking of knitting, their amazing patterns as we continue investigating how art and math tie together around the world. Again, thank you so much for watching, and on behalf of Region 9 and the Arts Council of Wichita Falls, Inc., thank you and have a great day.